Okay, we've now set up our coordinate system here. Sun is still at the origin. Prior to this, we only said origin, and we're thinking of a plane, but now we're going into the XYZ axis. And we set it up so that the z-axis was going to be aligned with this constant h vector we've been working with on this whole proof. And then we also had this constant of integration we just came up with, this c constant, and that's in the xy plane. It's in the plane of orbit. And we're going to line this up along the x-axis. After all, we can set up the x-axis any way we want. We're choosing to do it this way, okay? And so then our r vector, right, here's the orbit of the planet shown here, and the r vector points to the planet itself. And what we're going to do is we're going to set up an angle theta. And the angle theta then is going to be between the planet position vector r and the constant c vector. So in other words, this right here, that's theta. And so by talking about, okay, we've got an angle theta from the x-axis, and we've got a position vector r, that gives us the coordinates of the planet to be r comma theta, where r is in fact, the magnitude of the position vector, just like it always has been, and then theta is the angle from the x-axis. So what we've done is we've now set the orbit of the planet in polar coordinates. All right? So the orbit of the planet is purely in polar coordinates. Now with that in mind, we're going to do another one of these, not my idea, but a Newton-inspired idea, of taking r dot v cross h. Again, not something you would just think of off the top of your head, I don't think. So we're doing this dot product position vector dotted with the cross product of v cross h. Okay. Now, remind you that in the last video, this v cross h vector we found to be gmu plus that c constant vector. So we're going to plug that in here and rewrite this then as r dot this new stuff gmu plus the constant vector. Okay, and now we'll distribute the dot product here. So we'll go, r dot gmu plus r dot c. Okay, so we have r dot gmu, g and m are constants. We'll just pull those up front. So we get gm scalar multiplied by r dot u plus r dot c. Okay. And rewrite with some of the other information we have here. We know r, the r position vector, is just the magnitude of r, little r, times the unit vector. So that's this r value dotted with u. You might see where we're going with that one. Maybe a little less obvious is what we're going to do next with the r dot c. R dot c, if you look at that, you're saying, okay, you've got a dot product between two vectors whose angle we know. We're going to use the definition of dot product. Okay, definition of dot product says, oh, it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Right, that's definition. So, a couple things we can simplify now. First of all, u dot u, you're taking a unit vector dotted with itself. It's 1. Nice. And so let's just rewrite this. We now have gm r plus magnitude of r plus times the magnitude of c times the cosine of theta. Then we're going to show in, well, I guess it has to be the next video since I'm limited to 5 minutes. We'll show in the next video then that r dot v cross h is also equal to the magnitude of h squared. And what we'll do is we'll set this part equal to the magnitude of h squared and come up with our grand results. So, next video.